Okay, welcome back. Sorry for the slight delay. Had a slight technical problem. Anyway, two, you showed up. That's good. What I want to do is going to kind of summarize what we got going on for the rest of the semester, just to give you a heads up. So let me share with you the schedule. Give me 1 second. All right. Okay, we got one more. All right, so I'm going to go to the Canvas schedule. Obviously, today is the 4th. So, but wait, a couple more people that can come in. Okay, so we're looking at the Canvas schedule, and you guys are here on blue. These are my other classes. So today's the 4th. Okay, obviously you have the lab number 9. Then next Friday we have no class. It is Veterans Day. Okay, so no class there. And then the 18th, we come back. What I'm going to plan to do today is do chapter 13, which is relatively short, and then jump into 14 a little bit. So we basically have 4 chapters, and we're going to have a few days left over. So we'll come back on the 18th after Veterans Day. And then the following week is Thanksgiving, so we have no class again. All right, so we're off for a couple of days, and then we come back December the 2nd, and that is lab number 11. And so let's go into December. And so here's the 2nd, and then the 9th, and then the 16th is the end of the semester. So into December, we have 2 days, the 2nd and the 9th. We have the last exam, number 5, that weekend. Okay. And then also on that Friday, you have the final exam, which is the last half of the labs for the lab part, and that will be due on the 9th. And then the following week, as I stated, is basically we'll be done with all the lectures and so forth. And I will be here if there's any questions. The final exam is due on the 16th, and not like we've been doing the other exams for the weekend, because the 16th is officially the last day of class. So it'll be due on that Friday. If for some reason it doesn't work for you, I can move it forward 1, maybe 2 days max, but I can't move it after the 16th. So please plan accordingly. Okay. And then also at that day is the last day you can turn in anything that you haven't done with respect to assignments. Remember, assignments are, even though they have due dates, they are open all the way to the 16th, but they do have a penalty once they're submitted after the due date. Okay. Now, a word about these homework, for example, they have 2 attempts. And so let's say you did the first attempt way back in the beginning of the semester, and you're somewhat happy with the grade. Well, you have one more attempt, and you want to go back and maybe up your grade on that a little bit better, and that's fine. You can do that. But remember, if you do the second attempt, Canvas will treat it as it was sent in later. They give you a penalty. So therefore, I'll send an email to this. If you do a second attempt for the assignments, like the homework, and the first one was turned in on time, and you do the second one, you get a better grade, and Canvas will automatically deduct some grades because of lateness, I would take off that lateness. If you did turn it in originally at the due date or before the due date, okay? Some people want to go back and they do the first attempt and they're happy with it, but then later on change their mind and want to do the second attempt, and that's fine, no problem. Canvas will keep the highest grade. The other aspect is the nomenclature. You notice that I put a 0 in there to give you a heads up to show you what effect it does to your grade. The last day you can do the nomenclature is on the 16th, okay? And some people didn't like the idea of me putting the 0 in, but I do it for a reason early in the semester, because in the past I would wait until the day school ended and students wouldn't attempt it, and then I put the grade in and they get freaked out because they were maybe on the border, and then boom, they got a low A, and they kicked them, that 10% kicked them down into the high B area, and now they only got a few hours to attempt it before it shuts down. So to prevent that from happening, a few weeks ago I put a 0 in there. Okay, just to give you a reminder that that grade can affect that 10% can affect your grade. If it doesn't, then if you're happy with that, do with what you're happy with. But it will affect your grade if you're on the border. Okay, it can actually push you up, or it can also bring it down a grade at 10%. So treat it accordingly. All right, so we basically have like 4 days that we're going to meet. So that includes chapter 3. So in those 4 days, we'll do 13, 14, 15, and 16. Now, 16 is not on the final. There is a homework for it. And my plan is get done with everything on the 9th, lecture-wise. If not before, maybe better even on the 2nd, because that gives you the 9th as an open day, study day, if you will. I'll be here and you can come with any questions, okay? So we'll see how it goes. I think we might, we will probably end up doing that, making the 9th a study day. All right. The other aspect is on, if you want, on this Tuesday, because it's election day, my Tuesday class is not meeting. That's my 1 o'clock class and my 4:15 class. Also, Chem 130, but they're at GCC. Since I made Tuesday a study day, you are more than welcome, if you have any questions, to drop on by. It's the same link, and ask a question, because they're dealing with the same topics you are. Okay, so FYI. So, and like I said, I got two sessions. One starts at 1 o'clock, and the other one starts at 4:15 on Tuesday. Okay, this coming Tuesday, election day. Let's see what else. Any questions, comments? No? All right. I hope everyone's doing okay this semester. This is probably going to be the last online classes that both campuses, SCC and GCC, will be offering. They may be offering a hybrid of sorts. I know next semester I'm back on campus. So we've been doing this for now, since the pandemic, right? It's 2 years now. Pros and cons with online. It's really allowed me to do certain things that I couldn't do face to face. So anyway, pros and cons. I think I'm going to still continue with some type of online, even though I'm on campus. So for those students that, for example, can't make it, they can't get to the campus, I'll still run my Zoom. We'll see how that works. Anyway, all right, well, let us jump into chapter 13. Any questions before I begin? All right, well, chapter 13. Chapter 13 deals with stoichiometry. We had just finished chapter 12 that we introduced the concept of a mole. Okay, and a mole is basically a number. It happens to be a very large number, 6.02 times 10 to the 23rd units. It I shouldn't say it doesn't. That the mole doesn't really have to do with chemistry or science. It's a number just like a dozen. A dozen. It happened to be a scientist who developed that number, but it's simply a number. Like there is 12 in a dozen. Okay. But the other aspect about the mole is this: is that when we do, there's a question. Um, can we do the labs a second time? Oh, no, all the labs are a single attempt. There's no time limit on them, and so you have, you can start it and come back um, anytime you want. So, the labs, the only thing that has second attempts are the homeworks. Okay. Any other questions? All right. All right. You're welcome. And so we're going to be doing calculations where we're going to have uh, uh, reactions, and I'm going to write a theoretical reaction here where we have, let's say, A plus B reacting to give us, I don't know, let's say we got AB compound, okay? And for whatever reason, maybe we got two A's and that gives us, we require two A's and maybe it's B could be a diatomic, anything. So anyway, we went through the reactions. We learned we first took names of compounds, put them together to make the formulas. Okay. Then from the formulas, they start reacting with each other. We talked about the 6 different types of reactions and learned how to balance them. And we came up with the coefficients for them, which is important because we need to have a balanced chemical reaction when we start talking about doing calculations. Okay. And so, for example, we may have something like for argument's sake, let's say we start with 10.0 grams of A for whatever reason, and we need to know how many grams of AB we make. Okay. Well, that's what we're striving for. We're trying to calculate, starting with 10 grams of A, assuming that we've got sufficient B for this reaction to proceed. And we need to calculate, well, how many grams of AB do we generate? Well, the thing is that we can't go directly from grams of A to grams of B. We have to use a common unit. And lo and behold, what that common unit is the mole. Okay. And so basically, what we do is we take the grams of A, convert that to moles of A, and then from the balanced chemical equation, that stoichiometric relationship, it's a 1-to-1 here, 1-to-2, two A's to one A to one B. That relationship then gets us 2 moles of, let's say, AB. Okay, I stated that wrong. Our relationship between A and the product is a 2-to-2 relationship. So the grams of A converted to grams of moles of A, then from a stoichiometric relationship gives us 2 moles of AB. And then from the molar mass of AB, guess what? We get grams of AB. So that's how we can calculate from A to B, or AB in this example. Okay. We go through the moles. The moles is the relationship. And those coefficients are the stoichiometry of that chemical reaction. And there's stoichiometric relationships all around us. For example, your vehicle, your car has 4 wheels. That stoichiometric relationship is 4 wheels for one of the frame, the car, right? A bicycle has a stoichiometric relationship of 2-to-1, 2 wheels for one bicycle frame. And obviously a unicycle, its relationship is simply 1 tire to 1 frame. It's a 1-to-1. So that is what we're talking about when we're talking about the stoichiometric relationship, which comes from the coefficients that we put into the equation when we balance that chemical equation. All right. So let's say, for example, we have this reaction where we have nitrogen monoxide, NO, reacting in the presence of oxygen to give us nitrogen dioxide. Okay, now those are the words of this reaction. So you could very readily be given that sentence or two describing that reaction. And then from that sentence or two, take that information and convert it to chemical formulas and hence the chemical reaction. Okay, so now, and then after you do that, you balance it. Now, some of the equations that balance, we use a trial and error method. We put a 2 here, see how that works, move over to the other side. We can play with the numbers until we got everything to balance, okay? So this one's balanced. There's 2 nitrogens on the left, 2 on the right. There are 4 oxygens total on the left and total 4 oxygens on the right, okay? And so now with those stoichiometric relationships or the coefficients, we can state that, we can say that 2 molecules of nitrogen monoxide require 1 molecule of oxygen to give us 2 molecules of nitrogen dioxide, okay? Now, if for some reason we actually start off with 10 molecules of NO, well, to keep that stoichiometric ratio consistent, that requires 5 molecules of oxygen, right? Because that relationship is still 10 to 5, 10 over 5 ratio is the same as the 2 over 1. And then that also would generate us with 10 molecules of nitrogen dioxide. So when we talk about individual molecules, that we apply the coefficients from the balanced chemical equation. But in reality, we're not really dealing with individual molecules. We are dealing with Avogadro-sized numbers, okay? 6.02 times 10 to the 23rd molecules. So what we can do is remove the molecule symbol and put moles and say 2 moles of nitrogen monoxide require 1 mole of oxygen, which then produces 2 moles of nitrogen dioxide, okay? Now, having this balanced chemical equation, the relationship between NO and oxygen is a 2 to 1. So we can write that ratio in this form with NO on the numerator, or we can write it with oxygen in the numerator, just invert it, okay? And that is the relationship between the 2 reactants. We could do the same not only for the reactants, but from the reactants to the products. So the ratio of oxygen to nitrogen dioxide is a 1 to 2, okay? Or 2 to 1 if we're going from nitrogen dioxide to oxygen, depending on how we're stating making the statement. And from NO to nitrogen dioxide is simply a 2 to 2, or you can see as simply a 1 to 1 relationship, okay? And in both cases, in all of these cases, we can write a ratio. Now, which one we use depends on the question. And we're going to be using the technique we had worked with way back when we were converting units. That's why we introduced that chapter about converting units. We use that factored label system where all the conversion factors can be set up as a ratio. And then by keeping track of your units, you can set your problem up properly to cancel things out unit-wise. And so if we're given oxygen, so X moles of O2, and we're looking for nitrogen monoxide, well, then we will use this relation because our O2s cancel. You see that, leaving us with units of NO in the numerator. And vice versa, if we're given X moles of NO, then we would use the one on the right because we're striving to look for oxygen. Okay. Excuse me. Now, the second reaction could be stated as nitrogen in the presence of hydrogen gas, or nitrogen gas in the presence of hydrogen gas reacts to give us ammonia, okay, NH3. You'll see ammonia quite a bit, so you might as well memorize that formula, NH3, okay. All right, so we have a balance, and that equation, the coefficient tells us that we have 1 mole of nitrogen gas requires 3 moles of hydrogen gas to yield 2 moles of ammonia. Okay, and that stoichiometric relationship is true for that reaction, and for the calculations, we would use that stoichiometric relationship between the reactants and the products if we were doing the calculations for lab scale, or maybe we're doing it for industrial scale, like a plant out there where we have to make tons of ammonia, because ammonia is a very key ingredient in making excuse me, fertilizer. Okay, and so that relationship is true. Just larger scale, you have different problems, and that's where the chem engineer comes into play. In the lab, you move a beaker from point A to point B, but out there in the industrial plant, I got 10 tons of nitrogen. I got to move it over to the reaction container. What do I use? What kind of equipment I use, and so forth. Okay, totally different problem set, same chemistry. Okay, so the coefficients allows us to do mole ratios. Okay, and these mole ratios are utilized to do calculations, chemical calculations. So let's take, for example, this reaction. This reaction is iron 3 oxide in the presence of carbon monoxide reacts to yield iron and carbon dioxide. Okay. Actually, it's a very good way to get rid of a poisonous gas, carbon monoxide. But you convert carbon dioxide, which can pose a problem in itself. Okay. Using iron 3 oxide, aka rust. All right, so we have a balanced chemical reaction where it says that 1 mole of iron 3 oxide requires 3 moles of carbon monoxide to yield 2 moles of iron, okay, and 3 moles of carbon dioxide. You can see here our relationship, the stoichiometric relationship between the iron 3 oxide could be written in this form, or it can be written in this form, okay? Which one we utilize depends on the question. We also have a relationship between the iron and the carbon monoxide, okay? And this is ratio, or we can invert it. So you have, here you have one relationship right here between reactants. And so that's 2 ratios right there, okay? Then you have a relationship between one of the reactants and one of the products. Okay, so that's 2 ratios there. And then carbon monoxide and carbon dioxide. That's another 2 ratios that you can create. So that's 2, 4, 6 right now. And then with the iron 3 oxide to the product, that's 2 more ratios. So it's 2, 4, 6, 8. And then the iron oxide to carbon dioxide, 2 more. Okay, so we have a total of 2, 4, 6, 8, 10 ratios. And then you also have the relationship, the stoichiometric relationship between iron and the products, iron and carbon dioxide. So you have a total of 12 ratios that you can utilize and in your calculations. And which one you use depends on the question. All right, so let's clear the mess up here, and let's do a couple of examples. Okay, so first question here says, how many moles? Okay, right now we're going to be working with moles. We're going to go from moles to moles, but keeping back in your mind that in the lab we don't measure in moles, we measure in grams. So if you think about this, if we know the molar mass of a chemical, we can calculate the grams of that chemical and convert it to moles, and which we'll be doing. But right now, let's just work on the mole part, okay? All right, so we're asked a question. How many moles of iron Okay, so I have the balanced chemical equation up here, so I'm thinking about iron here. So I circle that just to tell me what I'm looking for because they want to know how many moles. So we're trying to determine how many moles of iron can be formed from 10.2 moles of carbon monoxide. So the only two entities that we are concerned about is in this reaction are between the carbon monoxide and iron. What is happening to the other species, we're not concerned about, just between what the work is telling us. And so here it says 10.02 moles of carbon monoxide will give us how many moles of iron, okay? All right, so as we've done before with the conversion chapter, units and so forth, we write down what we are given. 10.2 moles of carbon monoxide. And we write down what we're looking for, okay? That is our map to tell us we're going in the right direction. We're looking for moles of iron, okay? Well, obviously we're gonna have a conversion factor here, and we're gonna rely on the chemical reaction to tell us what that ratio is, because we want carbon monoxide in the denominator of that ratio, right? Because when we multiply this out, we want CO to cancel out, just like we did the conversion factors way back when. And we want iron to be in the numerator because that is what we're looking for, okay? So from the balanced chemical equation, we introduce the coefficients. Okay, and sometimes people are tempted to just take the 2/3 and divide that. My suggestion, just keep the coefficients as they are. Okay, sometimes you might forget. I've seen it before. Yes, you can take the 2/3 and get a fraction, and that works, okay, in the math. And you can do that. But sometimes I've seen the opposite where people took 3/2 ratio. So to alleviate any of those problems, just keep the numbers coefficients as they are. Okay. And you won't have any problems. Now we check our units. They cancel, leaving now the units of iron. So you can see how we went from moles of carbon monoxide. Now we've gone to moles of iron. And we did that because we have a balanced chemical reaction that gives us a stoichiometric relationship between carbon monoxide and iron. Okay? All right. So there you go. Check the units here. You can see moles of carbon monoxide cancel out, so you set that up properly. Don't forget your sig figs. Sig figs haven't gone away. Significant figures will always play a role in chemistry, in science in general, from day one to the last day, okay? And so 10.2 has 3 sig figs, so your answer should be no more than 3 sig fig accuracy. The coefficients here are exact numbers, so play no role in determining your sig figs, as the molar masses play no role because the atomic weights are the weighted average of whole numbers of the isotopes and so forth. So they have an infinite number of sig figs, so they're not used to determine your measurements, your actual measurements and the accuracy. Okay. Second question says, how many moles of iron 3 oxide? Okay, so we're thinking about iron 3 oxide here, are needed to form 70 moles of carbon dioxide. So we need, for whatever reason, we need to make 17 moles of carbon dioxide, and we need to figure out how many moles of iron 3 oxide we need to start off with. Okay, so our only concern is between the iron 3 oxide and the carbon dioxide. We don't have any concern about the other players in this reaction, okay? And I do that because I think what happens sometimes it makes the question confusing because you have those other two variables that are in there, and you're like, well, what do I do with this? Well, you don't do anything with them because the question is only concerned about is the iron 3 oxide and carbon dioxide. Okay, and we assume that the other material is there in sufficient amount in quantity for the reaction to proceed. All right. So then, as we did for number one, we write down what we're given as 17 moles of carbon dioxide. We know we have a conversion factor going on here, and we're looking for moles of iron 3 oxide, okay? And so obviously CO2 goes in the denominator and iron 3 oxide goes in the numerator because we want CO2 to cancel. And we get these coefficients from the balanced chemical equation, and it's 1 iron 3 oxide for every 3 carbon dioxides, okay? So it's 17 divided by 3, and that would tell you how many moles of iron 3 oxide you need to make 17 moles of carbon dioxide. And you're going to need a third of the amount of carbon dioxide, 5.7 moles of iron 3 oxide. And again, as I stated earlier, this is true if I want to make just 17 moles of carbon dioxide, or I want to make this type of calculation is true whether it's 17 moles or 17 million moles. Okay, obviously our number would be bigger, than 5.7, but it'd be a third of 17 million. 5.7 million moles of iron 3 oxide. That same ratio occurs. Is true, I should say. All right. All right, here we have an example where you're being asked to take this reaction of sulfur dioxide in the presence of oxygen, reacts to form sulfur trioxide. Okay, so we balance it, and unfortunately it's one of these that you do a little trial and error. So what if we put up a 2 there, because I see that there's 4 oxygens on the left and there's only 3 on the right. So what if I kind of put everything into even numbers, okay? And so if I put a 2 in front of SO3, now I got 6 oxygen, okay? And it kicks up my sulfur to 2, so no problem. I put a 2 in front of sulfur dioxide, and that takes care of my sulfurs, and at the same time, guess what? It takes care of my oxygen. Now I have 6 O2 oxygens on the left, 4 of them are in the form of sulfur dioxide, and 2 of them are in the form of oxygen, okay? So now we have a balanced chemical equation. We look at the problem. It says how many moles of sulfur trioxide, so we're looking at the product, will form if we start off with 16 moles of oxygen. So we are looking at the relationship between the oxygen at 0.165 moles and sulfur trioxide. So we're not concerned about what's going on over there, okay? All right, like we did before, we write down what we are given, and we have moles of O2. Obviously, we're going to have a conversion factor. We are looking for moles of sulfur trioxide. So SO3 goes in the numerator, O2 goes in the denominator, and from the balanced chemical equation, it's a 2-to-1 relationship, stoichiometric relationship. And so we just do the math, check our units. O2's cancel, leaving us with units of SO3. And we get the problem set up properly. And that ends up to be twice the amount of oxygen, or 0.33 moles of sulfur trioxide. So if I start off with 0.16 moles of oxygen and I have plenty of SO2, I would generate theoretically 0.133 moles of sulfur dioxide. And I say theoretically because here's the deal. This is what our calculation tells us that we need to use. And there's going to be plenty of SO2 in there, okay, so to react. So we need 0.165 moles of sulfur oxygen. It would generate 0.33 moles, theoretically. And that's assuming 100% reaction. Well, what happens in reality when you're in the lab, that very rarely do you get a reaction that comes near 100%. You know, you're always striving to get the best yield as possible. So what happens is you end up with a calculation where you get the actual yield after the reaction over the theoretical yield that you just calculated times 100. This is the theoretical yield, and this actual is what you actually measure out in the lab. And that gives you the percent yield. And that tells other scientists how well that reaction went. And you're striving to get as maximum yield as possible. I once worked with a chemical that was approximately, I forget, about $5,000 a gram. We got it from the National Cancer Institute, and we were trying to make a compound that could be used to be treated against certain cancers. And that material was, like I said, it's very expensive. And it's expensive because, one, it's difficult to make, and the yields are low. And they gave us about, I don't know, about 10 ounces of that material. So it was a lot of money there. But anyway, I was able to make it work and had to maximize it because you want to maximize your yields as much as possible. Anyway, just a little side note. And unfortunately, it's not always that easy. Okay, next question. Says, how many moles of sulfur dioxide, so we're talking about the SO2, are needed to make 0.042 moles of sulfur trioxide? Okay. So we need to make 0.042 moles of sulfur trioxide. So our concern is between the SO2 and the SO3, and we're not worried about that guy, oxygen. Okay. Note the stoichiometric relationship. It's a 2 to 2, which mathematically you can see it's going to cancel out, give you a 1 to 1. So, but my suggestion, until you're comfortable with these ratios, that just keep the coefficients as is. So we write down what we've been given, no different than before, of sulfur trioxide. Okay. Write down what we're looking for, moles of sulfur dioxide. So we want the trioxide in the denominator and the dioxide in the numerator. And it's a 2 to 2 based on the balanced chemical equation. You can see that the 2's cancel out, all right? So the amount of sulfur trioxide is the same for the amount of sulfur dioxide. It's a 1-to-1 relationship. All right. Okay, so here's a flow chart. We're going to give you another flow chart here to kind of put the whole calculations that we'll be doing in perspective. Okay, and my suggestion is in the beginning to use this flow chart to help you navigate through these chemical calculations. Okay, and use them as follow the steps. I always advocate to do a systematic approach to solving your problem, and you should, once you become comfortable with that, then you can go right to the problem with not so much of having to step everything out. I make it analogous to learning how to ride a bicycle. I've known few people who've never ridden a bicycle, jump on it, and boom, they're off and running. And, it takes a little practice in the beginning, And eventually you're out there riding a bike, doing handstands and so forth. Okay. Same thing with his calculations. The same thing with mathematics in general. All right. So we've been talking about moles to moles, but now I'm adding the other uh, aspect of it is that in reality, we are not calculating anything in the lab in moles. We have balances that measure in grams. So we got to learn how to convert the grams that we have into the moles of what we are given. And then based on the balanced chemical equation, we can go on and determine or calculate the moles that we're looking for. And from its molar mass, put that moles into an actual weight. Okay. And so this flow chart is kind of puts it all together. The problem gives you a material, a reactant in grams. So you're given the grams. Now, if you know the molar mass, then remember the molar mass is simply looking at the formula, the correct formula, and that's where we've been, recall we were putting formulas together, and we needed to make sure we put them together. If they're ionic compounds, we needed to put them together in the right ratio. And then we added up the atomic weights for all the atoms in the structure, and that gave us the molar mass, which had the units of, remember, grams per mole. That's the units of molar mass. Like any ratio, it can be written as that or as moles per gram. Okay. So if you see that we got grams and we got to go to moles, we're going to use the bottom ratio because they're grams cancel. Okay. And that would give us the moles given based on the weight. We cannot go directly from grams of A to grams of B. I'm just going to call this A and this is going to B. We can't do that. We have to go through moles. Okay. So now we got the moles that we've been given, and then this guy right here comes from the balanced chemical equation. Okay, those are the coefficients of the reaction. And that ratio set up properly would then convert us from the moles that we've been given to the moles that we're looking for, that we're trying to find. Once we have that, and we have the molar mass, okay, which like before, is in units of moles per grams per mole or moles per gram. Notice that we're in moles now. We want to get to grams, so we're going to use the top ratio to get us to grams. And so if you think about the molar masses, if you're given grams and you want to get to moles, you are in fact dividing by the molar mass. And if you have moles and you want to get to grams, you are multiplying by the molar mass. Okay? That's in essence what you're doing. But if you don't see it, just keep track of the units and you have the problem set up properly. The point of all this is that you're going to have at least 3 conversion factors here to be given X grams of some hypothetical compound A, and we want to get to X grams of some hypothetical compound B. And you're going to set up 3 ratios. This molar mass is going to go here. The mole ratio is going to get is that one, and then the molar mass for the last one is that one. Okay? To get us into grams. Now, the other aspect is the molar volume that could play a role here if we are at STP. Okay, if we are at STP, we get the molar volume where you got 1 mole is equal to a volume of 1 mole of gas is equal to a volume of 22.4 liters. All right, so using this flow chart, let's work through some problems. Here we have iron 2 oxide in the presence of aluminum reacts to give us iron and aluminum oxide. So again, that could be written out, and then you take that information and convert it to a chemical reaction. Now, can you tell me what type of reaction this is that I've just shown here? Iron 2 oxide in the presence of aluminum reacts to give iron and aluminum oxide. Can anybody see what type of reaction this is? It's one of the 6 we talked about. And let me give you a hint. Activity series. Does that help? Takers? Well, look at the reaction. Okay, because these are typical type of questions that could come up any place where I gave in words what the reaction is, and then the next question would be statement would be balance the chemical reaction, and then what type of reaction does that represent? Okay, so we talked about one type that we had an ionic compound and an element. Look what's happened. The iron is going back to the element. So we have an ionic compound, and then we have an element, aluminum's element. And then what happens afterwards? The iron goes back to the element state, and the aluminum goes to the ionic state. So does that ring a bell? Single replacement. Very good, Debbie. That is correct. Single replacement reaction, you can look at the activity series. You'll see that aluminum is a lot more reactive than iron. And then you ask the question, is the most reactive metal in ionic form? And the answer is no. The aluminum is in elemental form, so reaction proceeds. Okay. All right. So there are a couple of questions here. The first one, there's going to be 2 parts. The first one says, calculate the mass of iron 2 oxide needed to react completely with 5.55 grams of aluminum. So our concern are the reactants. If you start off with 5.55 grams of aluminum, how many grams of iron 2 oxide you need to weigh out to get this reaction proceed? That's in essence what I'm telling you. Nothing is asked about the products. We're just looking at the relationship between the reactants. Okay. Now, there's 2 parts here. I should have break them up. I think I'll fix this. But the second part of the question is this. Calculate the mass of one of the products, specifically aluminum oxide. So how many grams of aluminum oxide are you going to produce if you start off with 10.25 grams of aluminum? And so again, our relationship that we're looking at is simply between aluminum and aluminum oxide. And that stoichiometric relationship is a 2-to-1 relationship. Okay. All right. So the first one is going from the reactant. So as I stated, we want to know between these 2, the reactants. So we start off with 5.5 grams of aluminum. Okay. You need, first step is we need to convert 2 moles of aluminum. So we need the atomic weight. I say atomic weight here because it's just the element. Okay. If it was a compound, then I would be using the term molar mass, but it's just the atomic weight. All right, so we need the atomic weight of aluminum to convert the 5.5 grams into moles of aluminum. And notice that we are dividing by the mole atomic weight. And the units at this point will give us moles of aluminum. Okay, but we are striving to figure out how many grams of iron 2 oxide we need. Okay, that's what we're looking for, so we don't lose track of that. So our next relationship is to convert the moles of aluminum to the product or the reactant that we're striving for, which is the iron 2 oxide. And that comes from the balanced chemical reaction, which is a 3:2 ratio, okay? And that is why it's so crucial that you balance that reaction properly, because if it's a 1-to-1 in your balance, or you forgot to balance it, or you didn't balance it correctly, you can see your number is going to be completely incorrect, okay? All right, so now at this point, with respect to just the units, we have units of iron, moles of iron 2 oxide. And if that was the question was being asked, we can stop there. Well, obviously it's not, because we need to be in grams. So we need one bit of information, and that is the molar mass of iron 3 oxide. Okay. And let me clear my mess a little bit. So you can see unit-wise, and that's what I mean, set this up. Grams of aluminum cancel, moles of aluminum cancel, moles of iron 2 oxide cancel, leaving us with units of grams of iron 2 oxide, which is what the question asked for. And so now you just plug those numbers in the calculator and be aware of your sig figs. But none of the factors here play a role in sig figs, just the original number, 5.55, because that is a measurement. Okay, so you need to have 3 sig figs in your answer. Okay, remember sig figs, when you're multiplying and dividing, your numbers should not have more significant figures than the least accurate number that you use. And here you use the 5.55. The other conversion factors are not utilized in determining sig figs. Okay, so to put everything in perspective now, that means that if you weighed out 5.5 grams in the lab of aluminum, you need a minimum of 22.2 grams of iron 2 oxide to get those two to react properly. Okay, that's in essence what we are calculating. And essentially, it's the same thing in the lab. Trying to, if we needed to write this, we needed to make iron for some reason, we would do the calculations the same way. To figure out if I start off with 5.5 grams of aluminum, how much iron 2 oxide do I need? Okay. All right. Next one is we were going from aluminum to aluminum oxide. Okay, so as in the first case, we need to convert the grams of aluminum to moles of aluminum. And then from the balanced chemical reaction, because remember, we're looking for grams of aluminum oxide. Our relationship that we're striving for is simply between the aluminum and aluminum oxide. Okay, we're not concerned about the other guys. All right, so that 1 to 2 comes from the balanced chemical equation. Notice my units. We are now at the moles of aluminum oxide and determining the molar mass of aluminum oxide. Now gets us to grams of aluminum oxide. Check the units, everything's canceling out properly. Do the math, keep track of your sig figs. And so if I start off with 10.25 grams of aluminum, I should make roughly, theoretically, 19.37 grams of aluminum oxide. Okay. All right. Any questions at this point? Right, so here is the flow chart that when you come into these type of problems, you should have it readily available so you can go through the steps to get from point A to point B, okay? The ones we just did, the two examples we did was going from grams given, looking for grams, trying to find. We couldn't go directly, cannot do that, okay? We have to go through moles, go through this direction, okay? So we started off with grams given the molar mass, we figure out how many moles that has. Then from the balance chemical equation, the mole ratio tells us how many moles we're looking for, okay? And then from that, we have the molar mass tell us how many grams we are trying to determine, okay? Okay, bear with me 1 second. All right. Now, that's going from grams to grams, but like I stated earlier, if you are at STP, you can also go into, and one of your products is a gas, and you're at STP, you can calculate that volume, okay? Go in the other direction. Clear this up here. Okay, I mean, we can start here and work our way down all the way over here, okay? Or work our way this direction. Or we can go backwards. Remember that these steps here go in both directions. So this flow chart just speaks volumes with respect to the calculations that we do, okay? And I totally can't overemphasize to print that out if you need it, and you have the PDF file for this chapter, print this flow chart out, or you may have in your textbook, and use it in aiding you to go through these calculations, okay? All right, now let's say, for example, you are given a reaction, again in words, it says write and balance the reaction of HCl aqueous and solid cobalt, okay? All right, so we need to write down what we're given in words into chemical formulas. All right, so we got solid cobalt. Now, an additional bit of information is this. They're telling you that cobalt's going to react. And when it does react, it's going to be in the +2 state. You have to be given that information because cobalt being a metal is now part of, recall the sweet 16 I talked about? Those 16 elements, those 16 metals that you know are 100%, they had a constant and exact oxidation number. There are 16 of them. Cobalt's not one of them, which means that they have a variable oxidation state. And having a variable oxidation state, it could be anywhere, but you have to be told. And they're telling you that nickel will be in the +2 state. All right, so let's write down the reactants. We got solid cobalt, and we have HCl, which is aqueous, so this will be called hydrochloric acid. If it wasn't aqueous, it would be called hydrogen chloride, okay? Reacts and something happens. Well, here's one of the products. They're telling you what's going to happen. They're telling you cobalt is in the +2, so let's write that down. Okay, now before I proceed, can anybody tell me what type of reaction you are working with here when you have cobalt in the presence of HCl? What do you think? I'll give you a hint. Activity series. Does that help out? But whenever I say activity series, a hint, there's only one option, and it's a single replacement reaction. but it's a little bit of a twist, okay? Because you might think, well, wait a minute, okay, you have the metal, the previous metal we had was ionic, okay? But remember, the activity series is relative to hydrogen. If you look at that scale, you'll see hydrogen in parentheses, okay? So the activity, the reactivity of all of these metals are relative to hydrogen. And so hydrogen is either in the salt form, ionic form, would be an H plus, or if it's the molecular form, should be H2. You also hopefully remember that all of the metals in the activity series, starting with magnesium, okay, and ending with lead, those are the ones right before hydrogen. The ones in bold in the activity series, let me call this up so you can see what I'm talking about. Zoom up a little bit. Okay, the metals in bold are extremely reactive, and they spontaneously react with water with no additional help. And when they do that, they react with metal, that metal, which I'm going to denote as, I don't know if I can draw it here, but I'm going to denote as metal. These metals here, lithium through sodium will be metal plus water react to give us hydrogen gas plus the metal hydroxide, okay? Because they're so reactive. So lithium and sodium do that. That's the first group. The second group, starting with magnesium to lead, notice there's hydrogen, okay? They don't react like the first group with water as reactive. They will hang in water, no problem. They require a little bit more vigorous conditions than acids. So those guys, I'm going to label as M plus, react with a proton, okay, which is normally could be HX. And what they do is they generate hydrogen gas and the metal X. And if it's H hydrochloric acid, it'd be the metal chloride, okay? And why is that? Because those metals are more reactive than hydrogen. And you ask the same question. Is that metal in ionic form? And the answer is no. Cobalt is right here. Cobalt is not in ionic form, it's in elemental form. So the reaction proceeds and cobalt replaces the hydrogen, and the hydrogen then goes on to the element form, okay? Then the metals above hydrogen, copper to gold, they don't react with anything. They don't react with acid. Long term they will, but they require more aggressive acids to get them to react, okay? And so what we have here now, does everybody see how that is a single replacement reaction? So we get hydrogen gas, plus we've been told that we get the cobalt as CO plus 2. We write them first as ions, and then we got the chlorides here. Okay, so I need 2 chlorides. And so our formula for cobalt chloride, cobalt 2 chloride, is COCl2. Okay. Now to balance it, we put a 2 in front of HCl. That balances our Cls. Our hydrogens are balanced, our cobalts are balanced. And if we look at the solubility of cobalt 2 chloride, you see that all chlorides are soluble, except for a few select few, and cobalt's not one of them. Okay? So we wrote the reaction based on what we're given. We use the activity series to help us determine what the products were. And then as far as the physical states, we use the solubility to determine the solubility of cobalt chloride. And we know hydrogen is a gas, so automatically we put G. All right. And then we balanced it. Okay. So it's a typical type of question, write it out in words, give you additional information if you need it, write down the chemical equation, and then balance it, because the next step would be questions. All right, so now we have an additional part about this is now we're talking about STP, okay? And so now they're asking us this: how many liters of gas? Well, obviously the only gas here is hydrogen, and we need to know how many liters of gas will form if you have 5 grams of cobalt to react. So if 5 grams of cobalt reacted, how many liters of hydrogen gas are generated? And that means that everybody else we're not worried about. Okay, we're only concerned between the relationship of cobalt and hydrogen. Okay, so if you go to the flow chart, okay, you can see grams given upper left corner right here, and we're going to the volume that we're looking for. So we're going to using the flow chart. So notice here, from the grams given of cobalt, we're going to need the molar mass to give us the moles given. And then from the balanced chemical equation, we need the mole ratio to give us moles that we're looking for. And then the fact that we are at STP, we can utilize that relationship of 24.4 liters per mole, which is another ratio, to give us volume of gas, in this case, hydrogen gas. All right, so let me erase my mess here. All right, so we write down what we're given, okay? I should also write down what we're looking for. You want to know how many liters of H2 hydrogen gas are generated if we start off with 5.00 grams of cobalt. Okay, so we need the atomic weight because it's an element. Okay, so we look that up, take it from the periodic table, which gives us moles of cobalt. And then keep it in mind that our only concern is between the hydrogen and the cobalt. We're not worried about the other guys because the question didn't ask anything about that. Okay, and so we need now the stoichiometric relationship between the hydrogen gas and the cobalt, which is a 1-to-1. Okay, and as you proceed with this, keep track of your units, cancel things out, making sure you set this up properly. So at this point, you are in moles of hydrogen. And since we're looking for liters, you can use the 22.4 liters relationship, okay? And again, moles cancel, leaving us with units of liters, and you have set that up properly, okay? All right, so let me punch that number out. Now, one thing about this, remember something with respect to sig figs. As I stated before, these mole ratios are exact numbers, so they will not play a role in determining sig figs, nor would the atomic weight molar mass, because the numbers come from an infinite number of sig figs, so we don't use those. The relationship of 22.4 liters, that is a measurement, okay? So it could play a role with respect to sig figs. In this case, it's not, because we got 3 sig figs at 5.00 and we got 3 sig figs at 22.4. So the answer should have no more than 3 sig figs, okay? But if you started off with 4 sig figs, then 22.4 liters would then determine the number of sig figs. if your starting given mass was greater in significant digits. All right. Oh. So now we end up with 1.90 liters of hydrogen gas. So that gives you kind of perspective is this. If you do this reaction with sufficient hydrochloric acid, which is an aqueous solution, and if you start off with 5 grams of cobalt, and then you let that reaction proceed, and you collect the hydrogen gas that is generated, you should get almost 2 liters of hydrogen gas. Okay, 1.90 liters of hydrogen gas. All right. Oh, excuse me. All right, we've got a few more slides, and then we'll tell you what. We'll take a quick break, and then we'll see where we're going to go with the next chapter. All right. Next question. If 2.374 liters of hydrogen gas is formed, how many grams of hydrochloric acid reacted? So let's say you ran the reaction, you collected the gas, and you measured it, and you collected 2.374 liters of hydrogen gas. So the question is, well, you didn't know how much HCl you used. We want to know how much you use. So the relationship is between the H2 gas and the HCl. The other ones are just bystanders. Okay? Note the stoichiometric relationship there, 2-to-1. All right, so as always, we write down what we're given, and we have 2.374 liters of hydrogen gas. We want to convert that to moles, okay? And so look at the, let me back it up here. Go look at the flow chart. We are volumes of gas given, bottom left corner, and we're trying to strive to figure out how many grams on top right corner. That's the direction that we're headed. Okay, bottom left corner to top right corner. Okay, so convert the liters of hydrogen gas to moles of hydrogen gas using the 22.4 liter per mole relationship. This could only happen if we are at STP, 1 atmosphere, and at 0 degrees Celsius. From that, we have moles of hydrogen gas, and using the stoichiometric relationship from the balance chemical equation, we now can convert to moles of HCl. Okay? And then finally from HCl, moles of HCl, using its molar mass, puts us into grams. Now, check yourself here, make sure that unit-wise, everything is falling in place. Liters cancel, moles of HCl cancel, leaving us with grams of HCl, which is what the question asks for, okay? And so that corresponds to 7.73 grams of HCl. Note the sig figs. We had 4 sig figs in the beginning, okay? But we end up with 3 sig figs. Why? Because the 22.4 could play a role in sig figs, and in this case it does. Okay, so 3 sig figs. Our answer should be no more than 3 sig figs. Here we're asked hydrogen HCl gas plus oxygen gas produce chlorine gas and water vapor. So everything's in the gas phase. Okay? So we have HCl gas, which would be hydrogen chloride. If it was an aqueous system, it'd be hydrochloric acid, plus oxygen, which we know is diatomic, produces is our arrow, chlorine gas, which is diatomic, plus H2O, also in the vapor phase. Okay, so everybody's in the gas phase. To balance it, we could add, say, a 2 in front of HCl. That balances our CLs, but it can, and we balance the hydrogens, but we end up with 2 oxygens in the left and only 1 in the right. So let's up it up a little bit. What if we put a 2 in front of H2O? Okay, that takes care of the oxygen, but that then kicks up my hydrogen to 4. So I erase that 2, put that 4 there. And in doing that, that kicks my chlorides up to 4. Okay, no problem. Put a 2 in front of Cl. Let's go back and check. 4 hydrogens, 4 hydrogens, 4 chlorides, 4 chlorides, 2 oxygens, 2 oxygens. Okay, we're balanced. Okay. Here we go. All right, so the question is, how many liters of chlorine gas can be formed if 3 liters of oxygen react completely at STP? Okay, so we got 3 liters of oxygen. We want to know how many liters of chlorine gas are created. Okay, we're just concerned about these 2 and not concerned about the others. All right, so we write down what we're given, as always, okay? We have 3 liters of oxygen. Convert that to moles because we want to go to moles, right? Then from the balanced chemical equation, we have a 2-to-1 ratio, 2 to chlorine to 1 oxygen. And that puts us in moles of chlorine, which then we want to get to liters of chlorine. So we introduce the 22.4 liters again, okay? And that being said, we do the math, and that turns out to be 6 liters of chlorine gas. Now, notice something interesting is this, and hope I'll show it to you, but if you don't see it, don't just do it stepwise like we've been doing systematic, okay? But you're at STP, and notice that the 22.4 liters cancel out on both sides of our units. So essentially, you're just needing the stoichiometric relationship between the gases if you are at STP and you're trying to calculate the liters of one gas with the liters of another gas, okay? You can just simply use the stoichiometric relationship to get you to where you need to get. Because you can see that the process of converting the liters to moles gets canceled out at the other end where we are taking the moles and trying to convert that back to liters. Okay, but if you don't see it, don't worry about it. I'm just pointing it out to you. You probably see it as you do more of these, and things will cancel out properly. Okay, let us all right, what I'm going to do is try these at home. This would be perfect to try these at home. If you take 15 grams of carbon, okay, so the question is this: carbon reacts with oxygen to form carbon monoxide, okay? And then with that being said, how many liters of carbon monoxide at STP can be made from if you start off with 15 grams of carbon? And the second question, how many liters of carbon monoxide at STP can be formed if you start off with 20 liters of oxygen? Okay, so try these at home. See how you can get it. I got the answers there, but I'm not going to show you. I'm just going to tell you very quickly, and I'm going to zip on. You should get 28.0 liters of carbon monoxide and 40 for the second one, okay? Anyway, that was quick. It's not like you don't have that slide. You do have it. So anyway, the takeaway for this particular chapter with respect to conversions, chemical reactions is 1.1 is you need to convert everything to moles. If I want to get from grams of A to grams of B, the only way to do that is to go through moles. So I got to take the grams of A, convert that to moles of A, which normally ends up done by its molar mass or atomic weight. And then using the stoichiometric relationship in the reaction will get me to moles of B. And then from its atomic weight slash molar mass gives me 2 grams. If I'm at STP, then I can go down to the volumes here shown here in the bottom left and bottom right to do calculations dealing with volumes. Okay, so that flow chart, very important in these type of calculations. All right, well, with that being said, congratulations, you are done with chapter 13. It looks like we lost a couple people. Why don't we take a quick break? Maybe about 20 minutes. I got to check on my kid, and I got we'll come back at say 3:15ish. Yeah, 3:15. And then if you have any questions, we can go over it. And if not, I can start. I won't do the full chapter. I'll probably do maybe about 10 slides of 13. And then we'll just call it a day there. Okay? Just to make sure that we have enough of that chapter in so we won't be scrambling at the end of the session, because the next chapter does take a little time. Not a lot, but more so than this one. Okay? All right. So 13's done. Let's stop first. We'll come back at about 15, 20 minutes.